A very warm greeting to everyone who is watching this recording. I hope you stay warm and safe during the winter and during this COVID period. My name is Lu Tong Lun. I'm a firmware engineer in Intel Internet of Things Group. Today, I'm going to share about the open source firmware development model for the Programmable Service Engine in Intel Atom x6000E series. Below is the agenda of this presentation. First, I'm going to introduce what is Programmable Service Engine, as this is a new term to most of you. To make it easy, I will just call it PSE in my following presentation. Then I will talk about how the PSE relates to the current Intel firmware solutions. And moving next, I'm also going to cover the boot flow, where PSE firmware resides, the open source tool supports that we provide for this technology, the PSE firmware development model, and last but not least, the future and the key takeaway from this presentation. All right, without further ado, let the fun begin. So if you pay attention to the recent Atom series product announcement, particularly in December this year, right, Intel actually announced a new line of processor called Alpha Lake. There's a lot of interesting features that comes along with this line of processor. However, in this presentation, I'm not going to be able to cover everything, right? So I'm just going to zoom in to particularly the PSE. And in my opinion, this is probably the most interesting piece too. PSE is a new IP in Alpha Lake that is based on ARM Cortex M7. There's a whole subsystem in the IP that enable it to support a lot of things. So firstly, of course, is the I/O capabilities. If you look into the link that I attached here on the top, you can see that there is a couple of I/Os that is being exposed from the PSE, which means there's a lot of the real-time I/O capabilities that we can essentially play with. Like for example, the SPI, the I2C, QEP, PWM, just to name a few, right? Since it's going to be supported from Zephyr, which is an open source real-time operating system. So other than I/O, PSE can also support a couple of different features. For example, the in-band and out-of-band manageability, the 2.5 GBE TSN time-sensitive network technology. For the in-band and out-of-band manageability, this means you can essentially use the PSE engine to turn on and off the platform. As for the TSN, the Alpha Lake supports 3 GPE TSN, which 2 of them can be configured by the PSE. So from the features that I just described, I bet you can see that there's a lot of opportunities that you can do along the line of industrial and robotic use cases, right? Real-time I/O, manageability, and fast and real-time network. In the previous platforms, before this PSE comes to play, there is ISH, which stands for Integrated Sensor Hub. I believe a lot of you will be familiar with this even in your PC, right? So with this ISH, the typical use cases are usually in the OS level drivers for your sensors module in the PC environment. With the Zephyr enabled PSE firmware, there's a lot that you can play with, and it sets apart from the previous ISH, and this has more interesting use cases that is IoT friendly. Moving next, I'm going to talk about the interoperability between Intel boot firmware solution with the PSE firmware. The good news is the Alpha Lake release is going to come with the UEFI BIOS, the core boot, and the slim bootloader. So we have 3 different firmware boot solutions. As you would probably know, PSE IP is part of the new processor. So its initialization is going to reside in the firmware code, such as the BIOS and the bootloader. So during the boot process, the PSE firmware is going to be loaded from the Intel firmware to the ARM Cortex M7. Then the ARM Cortex M7 ROM code will essentially jump to execute the firmware. So your firmware can consist of your applications, and power management stuff. You can actually buy the Intel boot firmware. The PSE firmware is placed in the BIOS region. For Coreboot and other open source firmware solution is equivalent file system. For example, for Coreboot is Coreboot file system. So Coreboot can just take the PSE firmware pointers as a parameter and load it to the FSP silicon. The FSP silicon will then load it to the M7 during boot. So here in these slides, I've attached the Coreboot patch as well, so that you can have a look on how it works. All right, so as you can see here, so this is an example of the Coreboot patch to enable the PSE firmware loading. So from the code, you can see that it's just passing the PSE binaries that's being loaded from the Coreboot file system as a pointer to the region base address along with the PSE firmware size. So once you develop your PSE firmware, all you need to do is just put it as the Coreboot file system and then cast these two parameters. And there you go. You will be able to get your PSE firmware up. Moving next. Another interesting things about this PSE is that the I/O can be either configured to be owned by the host or the PSE from PSE IP, right? So this is actually done through the FSP parameters. And as we know, the I/O's control is going to be mutually exclusive. That means it can either be configured by one or another. So here I'm just going to take another quick glance through on the code on how to do that. So as you can see here, all the I/Os enabled is actually being exposed as a parameters, and this can be used as a reference for your design. For example, if you want to set it to owned by the PSE for real-time capabilities, you can just cast it to PSE config PSE own. Whereas if you want it to be disabled, you can just disable the I/O. And if you want it to be owned by host, you can also cast it to host own. Okay. So going next. I've also put together some diagrams just to help you better imagine how the PSE firmware and the data blob is being stored. So if you look at the left diagram here, these are all the Intel firmware solutions for Alpha Lake. For example, we have BIOS, the Slim bootloader, and Coreboot. For BIOS in particular, you can see that the PSE firmware is stored as part of the BIOS binary. So does the PSE data. And the same payload here could also be stored in the same structure with Slim bootloader and Coreboot. So during the boot process at the right side of the slides, you can see that the BSP gets out the reset, then it passes to the FSPM for memory initialization. After that, it moves to FSPS, and this is where all the PSE firmware is being loaded. And then your BSPs continue to boot to the OS. Concurrently, your PSE firmware is going to get loaded during FSPS. That means at first, when you get power on, the PSE ROM is going to get out the reset and wait for this parameter to be set. And once you set it, it's going to load the firmware from FSPS. So what I just described previously is how the PSE firmware sits inside the Intel firmware. However, what I did not cover is if you build the PSE firmware, what you're going to do about it, right? So here, Intel actually open sourced the tool support for the PSE development. So it's going to be an open source tool. And the link is shown here. So before I go into further details on the tools, so what these tools means is actually a SIIP tool. It stands for SoC independent IP. So what it means is SoC independent. So even though it's currently made for the PSE and Alpha Lake, some of them could be reusable for other platforms as well. So this provides the capability to stitch, sign, and generate capsules for your PLC firmware and data. So if you wish to develop the PLC firmware without having to deal with the complexity of Intel firmware development at all, or maybe you have a vendor, that does your BIOS development, right? You can actually explore these tools and the step-by-step guides on how to replace the PLC firmware in Intel firmware solutions. So all the scripts here are open source, and we welcome feedbacks and requests if you face issues on any of these tools. So I'm just gonna quickly show you how the tools looks like. So here in the GitHub, you'll be see that there's tools and there's some descriptions on the tools. Of course, with Python, there's some requirements on the modules that you need to install in order to execute it. So there's plenty of stuff here, but actually you can just use a H to actually see what is happening in the tools, and you can choose which subregions that you want to update if you want to use, a stitch tool or you want to use a capsule tool. So I'm going to walk you through one by one. Like for example, this command is going to call upon the zip stitch.py, and the IP here that's specified is PSE, and the output is going to be the binary, the IFE binary. And this is the input IFE, and this is your PSE firmware. So when you execute these scripts, what's happening under the hood is that this script is going to take the GUID of the PSE firmware, find it, and replace it. So it's really that simple for you if you have IFE on hand and you wish to replace the PSE firmware. As for the signing, so this also provides some examples on how you use these tools with your private keys and create a signed PSE firmware. So this also creates some kind of header for your PSE binaries. And as the tool is open source, so you are free to actually just take the tools, modify it, or implement your own security implementations. As for the subregion, these tools could actually just take your PSE firmware and create a capsule. So what happens is you can just issue a reboot after you generate the capsule, and in the subsequent boot, you'll be able to get your PSE firmware, a new PSE firmware loaded. So all the scripts here are actually stored in the zip2 folder. And if it goes to it, see the script here is all is in a Python format, so you feel free to use it, right? So if you face any difficulties, yes, you can just raise a questions, or you need some additional support, feel free. The stitch tool is able to locate the PSE firmware in the IFE using the GUID and replace it. So for example, if you are given a BIOS, or rather IFE for your platform, and you want to use the tool to replace the PSE firmware region. So what you can do is just take this stitch tool, execute it per the instructions shown in the GitHub, and you'll be able to replace the PSE firmware, so you don't have to deal with the complexity of rebuild your BIOS. There's also a signing tool that's used to construct the signed PSE firmware. So if you need a reference for your security implementation, you can use the sign tool. However, it's not strictly enforced. There's also another tool called the capsule tool. So imagine if you don't want to rebuild your BIOS, or you don't even want to stitch the IFE and refresh your firmware, you could use the capsule way to update your PSE firmware binary. So next, I'm going to talk about the PSE firmware development model. So the PSE firmware is actually based, and the reference code will be upstream in this link after Q1 2021. The code will come with the reference to be compiled for the different use case. For example, a simple hello world, out-of-band configuration, I/O configuration, the power management, and the 2GB engine for TSN. So imagine if you want to use this Alpha Lake board for your robotic application or your industrial application. So all you need to do here is first to build a PSC firmware from the Zypher project link here. After that, you can actually include the firmware code, firmware binaries that is being built, and put it inside your either Slim boot or Core boot or BIOS subregion. So for example, in this case, is a Core boot file system. So after it includes the firmware, you can either rebuild your binaries or you can use your capsule tool to create a capsule to update the firmware. And once you're done, your application will be able to run. There will be also a PSC UART that is able to capture any debug messages that you put inside your PSC firmware. So we have come to the end of this presentation. The key takeaway for this is that this new and great Intel Atom processor has an ARM-based microcontroller inside, which makes it interesting to create real-time IoT use cases. We will be open sourcing the Zephyr and the Intel firmware implementation like Core boot and Slim bootloader to enable this technology. Hoping to make this product more community friendly and get more interest in IoT prototyping, we humbly seek your opinions and your feedback and willing to improve upon your requests and questions. Thank you for giving your attention and stay safe, everyone.